Alright, here are two more examples of evaluating trig with inverse trig, and we're going to do it just like in the previous couple of videos where we use this flowchart here. So if you want to copy this flowchart to follow along with, check the video description here. There's a link inside the video description. You can click that link, open this up, and print this out, follow along if you'd like. So, example 5, inverse cosine of the cosine of 7 pi over 6. Okay, so start up here at the top. Is there a domain violation? No, there's not. Okay, so we follow the no branch. Why is there no domain violation? Because we can take the cosine of anything we want. Cosine is defined for all real numbers. The domain is all real numbers. So cosine of 7 pi over 6 is totally valid, totally legitimate, it's okay. Okay. So is there a domain violation? No. Is the function paired with its own inverse? Yes. Cosine is paired with cosine inverse, so the function is paired with its own inverse, cosine, cosine inverse. Okay. So is the function paired with its own inverse? Yes. Is it possible to cancel? Well, let's see. What was the rule for canceling with cosine and inverse cosine like that? So inverse cosine of cosine of x equals x if 0 is less than or equal to x is less than or equal to pi. Okay. But 7 pi over 6 is actually not between 0 and pi. 7 pi over 6 is just a little bit bigger than pi. Okay, a little bit bigger than pi. So that's too bad because we cannot cancel this. So actually this does not equal 7 pi over 6. Okay, so we cannot cancel this. Okay, so be very careful about that. Okay. So what do? Well, we just keep following the flowchart. So let's go back to the flowchart. Is it possible to cancel? No, so we follow the no path. Can the problem be solved using a unit circle? What does that mean? Well, another way of saying that, another way of asking that is this number in here, is that a nice number that appears somewhere on the unit circle? Yeah, 7 pi over 6, that's one of the nice angles on the unit circle, right? If we pull out a unit circle and check it out, we'll see that 7 pi over 6 is one of our nice angles in the third quadrant. So yes, since this is a nice angle on the unit circle and not some crazy goofy other number like 3.2 or whatever, then yes, it's a nice number on the unit circle, so yes, we can actually solve this with a unit circle. So yes, then go ahead and do it. So that's what we do then. Okay, so remember that cosine, so this is really just a matter of remembering the unit circle now. Remember cosine of 7 pi over 6, what is that? Well, it's in the third quadrant, so it's negative, right? Cosine of 7 pi over 6 is in the third quadrant, so it's negative. Cosine is negative in the third quadrant. So what this is going to be is negative root 3 over 2. Okay, so this is just a matter of knowing the unit circle. So then what we have is, since cosine of 7 pi over 6 is negative root 3 over 2, then inverse cosine of cosine of 7 pi over 6 is inverse cosine of negative root 3 over 2. Okay. So really at this point we're just evaluating this from the inside out. Okay. So cosine of 7 pi over 6 is negative root 3 over 2. So cosine of 7 pi over 6 gets replaced with negative root 3 over 2. And now we just do a problem like we did a few videos ago. We did problems like this where we just evaluate the inverse cosine of something. So remember, when you evaluate the inverse cosine of something, your answer has to be between 0 and pi. So basically, when we say inverse cosine of negative root 3 over 2, what we're really saying is which theta in this interval from 0 to pi has cosine of theta equal to negative root 3 over 2. And again, there are infinitely many thetas that have cosine of theta equal to negative root 3 over 2. For example, here's one of them, 7 pi over 6. But there's only one such theta that's in the interval from 0 to pi. And what theta is that? That theta is 5 pi over 6. Okay, cosine of 5 pi over 6 is negative root 3 over 2. And 5 pi over 6 is inside of this interval. So inverse cosine of negative root 3 over 2 is 5 pi over 6. Okay. And again, the reason is that when you evaluate inverse cosine, your answer has to be between 0 and pi. So when we say inverse cosine of negative root 3 over 2, what we really mean is which theta in this interval from 0 to pi, so between 0 and pi, has cosine of theta equal to negative root 3 over 2. And the answer is 5 pi over 6 because cosine of 5 pi over 6 is negative root 3 over 2 and 5 pi over 6 is between 0 and pi. Okay, okay, so that's example 5. Okay, how about example 6? So example 6, cosecant of the inverse tangent of 1. So go back up here. Is there a domain violation? No, there is no domain violation. So again, we're starting over at the top with a new problem here. There's no domain violation because we can take the inverse tangent of anything we want. Yeah, we can take the inverse tangent of anything we want. So inverse tangent of 1, that's totally fine, totally legitimate, totally okay. Okay, now I want to point out that there actually might be a domain violation later on. So when we do inverse tangent of 1, that has a specific value. And actually at this point, we're not really sure whether or not we can plug that value into cosecant, because cosecant has its own domain restrictions. So inverse tangent of 1 might give us a value that we cannot plug into cosecant. And as it turns out, that's actually not true. And I know when I teach this class, I don't trick my students with things like that. But just keep an eye out for something like that. It might be the case. What you can do is know that inverse tangent of 1 is pi over 4. Spoiler alert. And you can plug that into cosecant. Cosecant of pi over 4 is defined. Okay, but just be careful about that. Something like that might happen, but not in any of the examples that I do. Okay, so cosecant of inverse tangent of 1. Anyway, continuing. Is there a domain violation? No. Is the function paired with its own inverse? Well, here's cosecant, here's inverse tangent, so no, cosecant is not paired with its own inverse. Okay. So, in other words, the function is not paired with its own inverse. It's not tangent and inverse tangent. It's not cosecant and inverse cosecant. It's cosecant with inverse tangent. So, is the function paired with its own inverse? No. Can the problem be solved using a unit circle? In other words, does this give us a nice number from the unit circle? And yes, we actually already kind of gave it away, but inverse tangent of 1 is pi over 4. So we can evaluate that using a unit circle. So can the problem be solved using a unit circle? Yes, so we do it. Okay, so inverse tangent of 1, we already said is pi over 4. Okay, because remember, when we say inverse tangent of 1, what we really mean is, so when we ask for the inverse tangent of 1, what we're asking for is which theta in the range of inverse tangents has tangent of theta equal to 1. Okay, so remember there are infinitely many thetas whose tangent is 1, but only one such theta is inside of this interval, and that theta is pi over 4. Okay, so tangent of pi over 4 is 1. And pi over 4 is inside of this interval from negative pi over 2 to positive pi over 2. Therefore, pi over 4 is the answer here for inverse tangent of 1. Okay, but we're not quite done yet, right? So inverse tangent of 1 is pi over 4, so then this problem becomes cosecant of pi over 4. And then that's just a matter of knowing the unit circle, knowing the special values, things like that. And remember that cosecant is the reciprocal of the sine, so that might help. But anyway, what it really comes down to is that cosecant of pi over 4 is the square root of 2. And that is our answer. Okay, so that's 2 more examples of evaluating trig with inverse trig using this flow chart here. Okay, and some more examples coming up in the next few videos.